So sorry to be so late this morning, guys. I'll begin with a word of prayer. Heavenly Father, we thank you for this day. Just pray you help us to use this time wisely, just to glorify you what we do, Lord, and just help the students to be able to learn from the first test. I don't like to teach students on the first test, but it can be a learning opportunity. So just if people are frustrated, help them to see past that and learn what they need to so they can do better in the final, Lord. In your name I pray. Amen. Yeah, so I have been picky on this test. I don't deny it. Let's see here. I suppose I was more, what's the word, verbose about my pickiness in certain problems, like this one. This one should have been a surprise to no one, right? I ranted for no less than 5 minutes about people's inability to do this problem and the fact that I've put it on every test for like 4 years. That should have been a hint. Of course, I counterbalanced that with various princess-bride-based doubting. But yes, not having studied this means that you, really haven't studied, just to be frank. Now, so let's see here. The principal mistake people made, and those people being people who studied and just didn't pick up on a nuance in their studying, which is easy enough to do. And so this is probably about 10 people in here did this. They said something like Aij transpose equals to Aj. And the thing is, this is not true because Aij is a number, which is 1 by 1. Have I zoomed out enough that you can see that? Hope I can't. Is it? If you can see me, you can see this. It's probably fine. Yeah. So Aij transpose is, this is false. In fact, this is equal to Aij because when you take the transpose of a number, you get the number back again. Transposition of numbers is just numbers again. 1 by 1 matrices transposed to themselves. What you wanted there was this, A transpose Ij. Now that is Aji, right? And so this is the principal mistake people made of those people who studied, right? The mistake people made not studying, well, those are more creative and varied. I can't really address them all here. Those mistakes are more. There was one student who had all of these steps, like this calculation, just immaculate, like this, to this, to this, to this, to this, to this. But none of this. I took off 3 points. Words are required. You must explain what you're doing in here, okay? Anyway, next problem. Any questions about the first one, actually? You guys probably don't have questions, but no? Excuse me. So, most of you did some kind of, row or column expansion, understandable. Time pressure of a test, you're not fishing for sneaky, triangular ways to do it. But since this is how I made up the problem, I revealed my true method, which namely was I took this matrix and I did a couple row swaps to get that, because I know it'll make a reasonably uncomplicated example, but still 4 by 4. Right. If I just make a random 4 by 4 matrix and ask you to calculate the determinant, that's just not nice, But anyway, the answer was minus 42. Many of you got this. Problem 3. I said find the solution set of this in Z7, and I asked what's the cardinality of the solution set. Now, I might not have even said that word in class once, but this is a word that you should have seen in your previous math education, right? And I'm pretty sure I say that word in the notes somewhere, right? Yeah. So if you've studied, that wasn't too much of a shock. Of course, if in the test you'd actually asked me what's cardinality, I probably would have told you it's the size of the set anyway. No one asked me, so I assume everyone knew. Anyway, you don't really need any kind of fancy solution technique for this one, right? So typically we like to solve for the first variables in terms of the last ones. That's our custom. Right? So x would actually be the pivot variable here. Y and z would be the non-pivot variables if you want to look at it. And that's a, I don't know what that is. Probably should blame Sperano for that. Or is that actually a, no, it's, what, I don't, it seems to be, at first it looks like a cut. It's actually not. It's some kind of like, no, it won't come off either. I don't know. Oh, well, that's there. So the point is that's x. I put that there. I put y and z there. Y and z are free to range over z7, which means they take 7 values. 7 squared is 49. So the cardinality, the size of the solution set is 49. By the way, it's interesting to note you can write the solution set as 6, 0, 0 plus the span of these two vectors. That kind of calculation will soon become important to you. That's why I put that remark there. But I didn't ask you to present your answer in that way because we just touched on this idea like one example. So I didn't think it was fair to ask you guys to do that on the test, right? Yeah. Oh, sure. So in this this vector right here that we've got y and z, right? And for different y and z, we definitely have different vectors, right? Because if you look at y and z over here, right, if even they would have to be repeated in order for it to be the same vector. So as many different combinations of, distinct choices of y and z there are, that's how many vectors there are. So y and z are both ranging over z7, which has 7 things in it. So it's, 7 times 7. It's 49. That's the number. It'd be like asking how many 2-letter words you can make from the English alphabet. I think there's just, whoa, 26 squared, right? I mean, assuming that they're all words, but it's a lot. There's a question about Scrabble statistics. Of the possible 2-letter English combinations, what percentage actually constitutes a Scrabble scoreable word? Like I know it is, at, but there's weirder ones, right? Okay, I digress. Here, almost everyone lost points. And the reason is pretty simple. And I understand you guys are learning, so it's easy enough to make this mistake. But what I've told you is the reduced row echelon form of this matrix is equal to that. That does not entitle you to the right to say that V1 is equal to 1, 0, 0, or that V2 is equal to 0, 1, 0, or that V3 is equal to 0, minus 2, or that A is equal to 1, 2, 0, or that B is equal to 3, 4, 0, or that C is equal to 0, 0, 1. They correspond. They are not equal. So what you have to do here is to use the column correspondence property to notice that, for example, A has to be equal to V1 plus 2V2 has to be equal to A because that same, this is what I'm meaning when I say by column correspondence property, there's this relation between the columns, right? Because, and you could take a point off my solution even, right? Because my solution would be improved if I said by column correspondence property comparing rows 1 and 2 and 4 of the reduced row echelon form, right? We find this linear correspondence between A and B because those are the corresponding columns in that, right? But you see, I can tell when you're not really using the column correspondence property when you do something like write. It's a dead giveaway. You guys will write A is equal to 1, 0, 0. And then you'll say by column correspondence property. But the thing is, you can say that, but you don't really mean it when you write A is equal to 1, 0, 0. Right? Or at least I can't tell. I can't search your heart. I mean, there's some of you who mean it more strongly and less strongly than others. Some of you just, I don't know. I can't judge your heart. I have to judge what you write. So there's that. But otherwise, the logic, I think most people had some idea here, and maybe they just were confused about the correspondence idea. Yeah? So I could see that you have some genesis of the idea that you need to have there, and that's good. But I had to take off something because, well, it's not true. Similar comments apply here. And now I can't see it anymore, but so some of you, if you had written this equation, if C equals this, if this has a solution, but that's impossible because this matrix up here says that that equation is inconsistent, then I wouldn't have taken off like 2 points. But if you just said, you just wrote the matrix up here, just the relevant columns, and then said inconsistent, that's not quite enough for me here. Because the whole problem is to explain how, if it's possible, if C is in there, right? So this equation certainly should be part of the conversation or something like that. And again, if you just write reducer echelon form of the matrix equals to what it is without some extra conversation, I really can't tell if you're using the correspondence or if you're still laboring under the confusion that those vectors are really the vectors which are given. Which is not a hypothetical confusion on my part. I've seen it manifestly written in your first part, many of you. Does that make sense? I know I was very frustrated when I took linear algebra 2, like the first time, that the professor sometimes took off points, and I was like, but I understood that, right? But he's critiquing what I'm writing. He's trying to help me improve the precision of what I'm writing. When we grade you guys in calculus, many times I will give you credit for having a fuzzy idea, even if it's not written exactly correctly, because I cannot afford to take away your points. And here, I must take away your points because we're trying to make you into good math majors who write things precisely. This is partly a proof writing class, and so these kinds of issues are more penalized than they would be elsewhere. Elsewhere, I'm really more focused on, do you just have the general idea? Here, the general idea is part of it, but writing it precisely and as you can is also part. Again, almost the same discussion here. Is this a linearly independent set? Well, that would mean that this equation only has the zero solution, right? But by the column correspondence property, this is the corresponding columns, right? Well, the grammar could be improved here, right? What I should probably say is this equal to 0 implies that. Hence, by the column correspondence property, this must also imply that these are 0, right? So my sentence is not ideal either. You could criticize it. But certainly the column correspondence property should be mentioned. I mean, anyway. But not just mentioned. Like, mentioning the column correspondence property but not showing me how it's utilized also doesn't work. Because there's a lot of you who will just start writing CCP on everything, much like, taxis in Haiti all have Jesus written on the side of them. It's not because they're Christians. It's because it's good luck. Taxi de Jésus. It's good luck. Because when I was a teenager, I went to Haiti, and I was like, why does it say Jesus on all the taxis here? It's like, oh, it's good luck. They also have stuff about, voodoo and other things on the taxi, if you know. But so CCP, it's not just a slogan. It means something. We need to understand its mechanics. That continues to be important throughout the course, because CCP is a way for us to calculate things without calculating things, right? I give you a row reduction. You can extract from it all kinds of information without actually calculating, which is nice, right? Because if I actually give you solving a 3x3 or a 4x4 on a test, that eats 10 minutes, right? Well, once you get the speed, it eats less. But for some of you, it'll always eat 10 minutes. And now this, so many people row reducing here. What's up with that? This is a 2x2 matrix problem. We have formulas for these. First of all, you want to use algebra to solve for x, right? So multiply by the inverse on that side, b on the other side. I happen to know b is its own inverse, b squared is I. So this is just multiplying by b inverse on the other side. And it's kind of funny. When you multiply this by b, it goes back to itself again, right? It's kind of funny. This is b plus I. But anyway, however, and lots of you got to this, right? And I would give you at least half credit if you got to that. But then And actually, I think at least a third of the class got this problem right, probably more, maybe half. And then the people who got it wrong, well, some people didn't get it wrong, but they got it wrong because they spent a half page of calculation to get this result. This shouldn't have been a major investment of your time, this problem, right? Some of you are doing this the very, very wrong way. Like I've seen some people writing down 4 equations and 4 unknowns and solving them. I admire your tenacity, but you're wasting your time on my test. That's why my test seems too long to you, because you spent way too long on this problem. You did not use the right technique for it. Again, if you have any questions, just interrupt me. Problem 6 should have been, easy picking for you guys. We have a theorem that had a list of equivalent conditions for invertibility of a matrix. One of those conditions was that AV equals to B has a unique solution for every choice of B. So I have 2, this is B, they're both equal, and yet V1 and V2 are not equal. That means that there's not a unique solution to the equation AV equals to B for some B, which means that the inverse does not exist, right? Which in the case of an infinite field means that the solution set's infinite, right? Because the reduced to echelon form is not the identity matrix. It has a row of zeros, which corresponds to there being at least one non-pivotal variable, which then implies the infinitely many solutions. So, yeah. So, I don't know, there's a lot of, I think, people just guessing stuff here. I think a lot of people who got wrong answers there did not hold those wrong answers deeply. They just wrote something and whatever. But, of course, another way of approaching that, of course, is just take the difference of V1 and V2, which I, I figured some of you might do because it's kind of in the same spirit of that homework problem we had to find the inverse of the matrix with the V1, the V2, V3, V4. This problem is similar to that in a regard. Of course, once you figured out the solution set's infinite, in other words, that the reduced row echelon form of the matrix is not equal to the identity, it then, of course, follows that the determinant must be 0, right? So this is not true. We don't have the unique solution to 0, which means that the determinant is not equal to 0, which leaves you that possibility, right? Because real numbers, well, they're either 0 or non-zero, right? This was interesting. I had a couple people give me the correct sketch of an induction proof, but no details to buttress the argument. So I was reading, this is, there's an induction claim. I take n, I imply n plus 1. The base case is true. It's like you stated the base case is true, but you did not actually write down the calculation which proves the base case is true. So, I mean, that's a good template, but we need to fill in this template with details, right? So the details that I need to see, in particular, are these. For the n equals 2 case, we have A1, A2 transpose as sock shoes. Oh, man, look at that. I don't know what happened right there. There's supposed to be a T right there. Look at that. I mean, it's not wrong, but it's not right. There's supposed to be a T there. I don't know what happened there. That's very disturbing, really. It's like yesterday I labeled, or the other day I labeled 2 axes both with Y. Like, where's that from? Like, I don't usually make that mistake. Why did I put a Y on the X and the Y axis? Why would I do that? It's not something I can fix, right? And these kind of errors happen more and more as I get older. It's not good. I need to get better students who can find my errors more quickly. Never big on grammar. Anyway, so the induction claim, it'd be nice if you labeled it, I labeled it with a star. This is the induction claim that, the product of symmetric matrices is symmetric. So then I consider n plus 1, consider the claim for n plus 1, basically. Sock shoes, and then, of course, the induction hypothesis is that, and then, of course, that's that. But we're given that this is symmetric, so that's, and then they commute, so I can reorder them. And there you go, this is symmetric. Now, some of you, and I couldn't fault you, found a way around doing induction here, because you just quoted the sock shoes rule for n matrices. And if you know the sock-shoes rule for n matrices, you don't need induction, because it follows from direct calculation with the n-fold sock-shoes rule. This, of course, was not my intention. What I wanted from this problem was an induction proof of yours. But as you can see, I failed to write, give a proper, meaningful induction proof for something in the problem statement. And as such, I left myself open for the El Cheeto, using of the n-fold sock-shoes rule, which is really against the spirit of this problem, but I have to respect, and because I did not rule it out, unfortunately. Now, if I was an older, grumpier professor, I might just take off points and say, you've violated the spirit of the problem. No. You should learn to have more mathematical taste. You should understand the spirit of the problem. I shouldn't have to say everything. And I do sometimes say that because I'm getting older and grumpier. But anyway. Now this one here, I was very happy with this problem. Very many people got this right. Even the people who got it wrong got it right. There's about 5 people in here who did all of this stuff, got all the way down to here, and then said crazy stuff like C1 equals to A, and then blah, blah, blah. You said everything that you need, everything that doesn't matter. The one thing I asked for was find the equation in ABC, which places this in here. The equation that you need is this guy, equals to 0. So on your test, if I circled that and set that equal to 0, I'm saying that's all that matters. All the stuff you have written down here, no, irrelevant. If I had asked a different question, relevant, but I didn't ask that question, so this is what you want. That, or, well, of course, this also works, right? And a lot of you got that, even if you didn't get it, because you still got this, but you just didn't know how to make the final kind of important logical step. I probably should have taken off more than 5, but oh well. I didn't. If you messed up a sign or something here, I took off 3 or 2, depending on the severity of your error. See? It's like a snare. All of a sudden, like I think all of a sudden I'll be lecturing, and then I'll be like upside down, hanging from the ceiling. The IT department will be like, haha, we got you. Hey, you know what? I'm also, for the most part, pretty happy about this. A lot of people got this. That's good. I mean, you really should. A lot of times I put this question first on the test, but I put it later because, there's a subset of you who will take a crazy amount of time to do this problem and then won't leave yourself time for other theoretical problems. That's why I put the theoretical problems first, so you wouldn't have an excuse. Hey. Yeah. Now, I think made got a couple of small errors. Not only one, really not many people doing this, but every so often I'll have students who just start leaving off parentheses here. That's problematic because then it's not a point in R5, which is where, R5, because I said R was the default, right? Other people have just put in curly brackets here and not put such that x4 and x5 are real numbers. That's not going to work for me. We state where the parameters come from over here. It's not understood in here. We don't use that abbreviated notation. Sorry if you used it elsewhere, but you never saw me use it. Oh, another important comment. That plus that is in fact the solution set. Seems like we can always write the solution set as some vector plus the span of a couple of other vectors, right? Where the number of vectors in the span is the number of parameters up here. Any questions? Now this, I hope you saw well, many of you didn't. And this also added to the length of your test unnecessarily, right? Because you should notice that if you put a bar right here, that this calculation tells you that the inverse of that matrix is that guy. Some of you noticed this. Some of you didn't. At some point in the calculation, it should have like popped out at you, though. I did put it on the same page. I tried. Yeah.
If we see that in a test, do we still have to like grade out the whole thing, or can we just be like, the work was already done here?
Right. You say by the previous problem's calculation, I know blah. Yeah. Why would I? No, I wouldn't want you to write the same. I mean, If you want to check your work, it wouldn't be dumb. Some of you did it for checking work's sake, and that's fine. A better way to check the work, though, would be just to multiply this times A and see if it works out to the identity, right? I mean, I did that in my initial calculation, and I found out I missed a sign here and here, personally. But a lot of you got this, and that was good. A lot of you didn't know what to do with it. You didn't know what I meant by solve this. That's troubling to me, that you don't know what I mean by solve this. When we say solve something, we mean to solve for the unknown, in this case, V. Let's see here. So we multiply by inverse, and of course that gives us this. Yeah. And a lot of you got that, so yay. So what's the point of this problem? The point of this problem is to collect together all of the various conversations I've had about what it means to multiply a matrix by the standard, like the EIJs or the, the select a column calculation or the select a row calculation. I put all of these things together in one foul new problem, here before unseen, right? So in particular, we talked about this, that if we multiply A times E13, what that does is it puts column 1 and column 3 and it zeroes out everything else. So when I look at this, I can immediately tell, oh, column 1 is 103. And I just re-derived that fact here, but anyway. So column 1 is that. Likewise, E3 transpose time A is row 3. So I've already told you that row 3 is 322, right? But I also told you that it's symmetric. So from the first row, first column and third row, I automatically get that this must match that, and that must match this, which just leaves one oddball. Excuse me, one out, which is x, the middle. All right. But the determinant being minus 11 fixes that to be 1. Not too many of you got this. Maybe about 5 people really got it all the way through. A lot of you got part of it. A lot of people got that the row 3 was this and that the column 3 was that from the symmetry. Less people understood what to do with this. That kind of doesn't surprise me. Problem 12 suffers from the same kind of problem as the reduced or echelon form question earlier, where you've assumed something about the matrix which isn't really given. This actually does not mean that A is diagonal. There are matrices which are not diagonal and yet permit vectors v1 through vn that have that. Now, it is true that if you look at the linear operator corresponding to multiplication by A, there is a basis in which the matrix of that transformation is diagonal. These things you guys don't know yet, right? So you can justifiably say that's not what you were thinking. So there will later be a diagonal matrix to be found. So your intuition's not completely off base, but we haven't filled that in yet. Anyway, so here it is. If you put these together in a matrix like that, well, these are given to be that, right? But then by the column by column rule, I can pull A out, and then I can take the determinant of both sides. Then I use the column by column linearity. I can pull constants out of each column one at a time rule for the determinant to pull out the 1 through n. But then this is non-zero, and that's non-zero because I gave you that these were linearly independent, which means that the matrix they make up is an invertible matrix which has non-zero determinant, which then means I can cancel this guy, and that just leaves me determinant A is equal to n factorial, which a couple of you got for the wrong reasons. So I give you half credit because it just seemed, I guess I should have taken off more because your reasoning was not legitimate. But I was just happy that you'd stumbled into the right answer. So now here, I'm open to other statements. Some people have stated that the column correspondence property says that A is, any linear dependence in the columns of A is related to the same linear dependence in the columns of the reduced or echelon form. I have, at many points in my teaching, said that that is the column correspondence property. So that's fine if you said that. But strictly speaking, there's this kind of more general one which just says that is a relation between any linear, it's a linear dependence must be preserved between any two row equivalent matrices. A and the reduced row echelon form are, of course, row equivalent. But the column correspondence property is more general than just that. That's really an application of the column correspondence property to say that A is row equivalent to the reduced row echelon form and to observe a linear dependence there. But again, I'm happy with that. I didn't take off points for that part of it. Now, if you said that the column correspondence property says that there's some sort of correspondence between linear dependence of the rows of A and the reduced row echelon form of A, well, that's just wrong. In fact, if you were to study linear dependence between rows of the original matrix and rows of the reduced matrix, there really is nothing nice to say there. Nothing. I mean, row, as we'll soon learn, row space is horribly mangled by row operations, but column space stays the same, whatever that means. All right. And then this is the proof that we went through. So, yeah. Any questions? Yes, no, maybe so? Well, you can talk to me individually in office hours after this, too, if you got something individual. I do sometimes misread your argument, and you might have meant something that I said, and I just read it differently. And I'm open to discussing things, you know. I'm not like some of my professors that I had when I was an undergraduate who, I showed them something on a test, and, the points have been taken off, and I was like, but this is correct. And he's like, yeah. I was like, okay, so can I have my 3 points back then? Out of 100 or something like that. And he's like, it's just 3 points. I was like, but I'm right. Yeah, it's just 3 points. And like, no, he would not budge. So that is not my MO. In retrospect, I respect him. I mean, I know what he was doing. It's something we're not allowed to do anymore because professors aren't respected in universities, largely speaking. So, unfortunately. I mean, the fact of the matter was it didn't matter because at the end of it, this guy curved everything. So he was aware of the fact if he'd made that error in my solution, my grading, he'd made that error in the rest of them, right? So it's unfair to just correct mine and not correct everybody else who hadn't come and complained about it. So, I mean, or it could just be that he doesn't want to encourage people coming to his office to quibble over points. So he didn't want to award me for my behavior. So I don't know. For me, it was, partly about the points, but it also was just about I wanted to understand if I was wrong really or not. So that kind of questioning I think should always be encouraged. All right, I said I would go over one of these proofs. So let me just go through one of these guys with you guys. And I have stupidly turned off the lights. Turned on the lights. Ah. Oh, you're good. All right, so the law of cancellation. So I want to just go through with you guys and talk about how we prove something so basic. All right. So we have AX and Y vectors in a vector space V, right? What does that mean? That means we're entitled to the list of the 10 axioms, right? That's all we have to work with. And here's the statement. If X plus A is equal to Y plus A, then X is equal to Y. All right. So here's the proof. We suppose X plus A is equal to Y plus A. All right. That's the, we're doing a direct proof, so that's the starting point. We assume what's this thing called? I don't know. You guys, if you've had Math 200 recently, you may remember the name of the direct. It's a direct proof, but what's the name of the thing you assume? Yeah. See, I know how to prove things, but I don't know the names of how to prove things. This is why I should teach Math 200 on occasion. Is it the precedent? Is it precedent and is it the antecedent? The premise? The premise. Okay, I don't know. See, there's a difference between knowing how to do something and knowing the name of the things that you're doing, right? It's even true for proofs. So, I am okay, so anyway, whether or not we can name this step, it's the correct step to start with. Assume what you're, assume the starting of the if-then, whatever that is called. Oh no, sad. I'm going to get YouTube comments. Anyway, okay, so by axiom 4, which is the zero exists axiom. Oh, I'm sorry. It's the additive inverse exists, right? There exists a minus a such that a plus minus a is 0, right? Thus, if I take this and I add minus a to both sides, I get that, right? Now, admittedly, I'm assuming that there's this thing we can do of adding something to both sides, right? So if you were like a foundational logic person, you probably could dissect this further, why I could add something to both sides. I'm not going to get that nuanced in here. So we add we add minus a to both sides. Then by axiom 2, right, we can reorder the addition like so by associativity, right? By associativity, I can regroup the addition like so. But then by definition of additive inverse, I get 0 and 0 here, right? But then by definition of 0, that gives me, oh, come on. No. X, right? You're not crazy. That should be X. X. So that gives us X equals to Y, and that's the claim. So yay, we have, and the thing is, so what's the point of this? The point of this is anytime you have that set of axioms, right, that automatically entitles you to cancellation. Whether it's functions or matrices of functions or any of that laundry list of examples we had, right? If you can establish the axioms for the vector space, then you get all of the theorems which follow. That, by the way, is the whole point of this, is that we're trying to focus on that like fundamental linear structure so that we can say things that are true for all things with that linear structure. That's the point of abstraction. It's labor saving. Rather than proving a theorem for all my examples, right? One at a time. You prove it for vector spaces. That means you've proved it for everything. That's the whole point of what we're doing. That's abstraction. Well, that's part of abstraction. To prove 1, what do I do here? 0 times x plus 0 is 0 times x. Well, that's because 0 is 0, right? Right? This first step makes sense? By axiom 3. I think axiom 3 was that 0 exists, right? And behaves as 0. If I remember right. Yeah. I should actually plug it. This has up-down features. If I actually plugged in the USB thing, I could be scrolling back and forth, but it's kind of above I can only really do one thing at a time. That's too much multitasking for me. So now 0, that's 0 in the field, right? The real number 0 plus the real number 0 is still the real number 0. That's going from here to here, right? 0 is 0 plus 0. But then we use the distributive property for scalar multiplication and vector. Scalar multiplication, sum of a scalars times a vector, that distributivity, which is axiom 8. And that gives us this. But then what's that say? That says that this is equal to that. And by cancellation, it must be that 0 is equal to 0 times x. Right? And the proofs of the rest are similar, but not especially exciting. But I'll let you read them. So I would encourage you to just, take 5 minutes to work through each one of these. If you do that, you should be well prepared for the test question if I was to ask it. Do you want to see what it looks like? I'll show you what it looks like last time I asked it, if I can find it. I think it was spring 14, I last asked this. Now, spring 14 was a little bit different. Where'd that thing go? Come on. Where you go? Oh man, that's not the one. Uno momento. If it wasn't spring 14, it must have been spring 15? Maybe? Where'd you go? Where'd you go? Come on. Says, no. No, that's not the one either. Dang it. Have I not had the patience to grade that problem since the first time I taught linear? I really do hate grading this problem. But I feel obligated to ask it on occasion. I feel like we're due. But still, push comes to shove, I might not put it on there. Because I hate grading. I just hate it. I hate grading it. I hate it so much. Come on, where'd you go? Ooh, true, possible, false. Ooh. Yeah, so, okay, so in 13, fall of 13, last time I asked this question, I will actually state the definition and then below it, ask you to prove that x times 0 is 0 from the definition. That's how I would ask this question if I was to ask it. I don't really expect you to have, I expect you, let me say it this way. I do expect you to have these memorized, but I don't expect you to have them memorized with the labels. I want you to have them memorized in the terms of the concept, in terms of the distributivity, the associativity, the commuting, the existence of 0, all those things you should know in your heart. It doesn't matter to me if you have them ordered in your heart. I don't expect your heart to be an ordered set, if that makes sense. I mean, all right, enough about this. Do you guys have questions about other things? All right. Then we should look at some subspace examples for you guys. Let's see, so I did one example last time, right? I showed you guys at the end of last class, we saw that the, what was it? The subset of symmetric matrices was a, what? Subspace? So another example of vector space would be, and so in my current notes I use P2R, but it occurs to me a better notation might be this. R of x and something like this. Or maybe we could get away with this. R less than or equal to, no. Where should I put the less than or equal to? I'm debating. What's the, so this is one of Dr. Smith and I's grumblings, is that there's no agreed upon universal notation for polynomials up to a certain order in a certain variable. But what I mean by this thing is of the form, let's say a2x squared plus a1x plus a naught, such that the coefficients a1, a naught, a1, a2 are real numbers, right? So this forms a vector space, right? This forms a vector space of quadratic polynomials. Now, if you're a very good student of pre-calculus, you should complain that I am not being precise. Are these quadratic polynomials? For example, I take a2 equal to 0, and I take a1 equal to 1. I take a naught equal to 1. That gives me x plus 1. Is this a quadratic polynomial? It is not, right? So when I say that this is the vector space of quadratic polynomials, I'm not being quite accurate, right? So if I'm feeling more legalistic in my terminology, I will say something like, it's the vector space of possibly degenerate quadratic polynomials. But some people will just say quadratic polynomials, right? But you should realize that's a lie, because we do allow the leading coefficient to be 0. Yeah? We have to. Otherwise, 0 is not in there, right? So the vector addition and the scalar multiplication is just what you'd expect, all right? We add polynomials like usual. We scalar multiply polynomials like usual. So here's, and also we can think of these as polynomial functions, right? I mean, we can think of this as f of x, right? Where what? For example, f of a is what? Well, f of you give me a letter. C. Excellent. Would be a2c squared plus a1c plus a naught, right? So there's a natural identification of polynomials with polynomial functions, which is helpful for us in examples like this, because we can exploit what we know about polynomial functions to look at these sorts of things. So what's a subspace? How about this? Let's look at W equal to f of x in P2. I'm still not. I'm trying to break myself with this P2 notation. F of x and R of x less than or equal to 2, such that f of 3 is equal to 0. Is this a subspace, and what does it look like? Yeah. So point number 1, W is by construction a subset of this vector space, right? So we definitely have that W is a subset. There's no ambiguity there. So I have a remark in the notes where I say that really the subspace test theorem is a 4-step process. Step number 1 is identifying that W is honest to goodness a subset of your vector space. A lot of times I don't even comment on that because it's just completely obvious from the context that it's a subset. And then what's next? The next thing is kind of hidden in the preamble of the subspace test theorem, is that W is non-empty. I assume W is non-empty in the subspace test theorem statement. But that is something you have to check for an actual example. How do you check that something's non-empty? For example, this room is non-empty because Emily is right there. So it just takes one, right? I could observe my own existence, but it's more exciting to observe a student's existence. So I'm not like Descartes, I don't doubt your existence. I think that's a stupid and useless discussion, actually, truth be told. If you doubt the existence of other people, why are you having conversations with other people? I'm sorry. I'm not a philosopher. What can I tell you? So point number 2, and so our go-to is to look for 0 in W, right? This has the benefit of if you can't find it, you've already disproved that it's a subspace, right? If 0 is not in there, game over, right? 0 has to be in there. It's because if it's a subspace, it has to be a vector space with respect to the ambient. So, so what's 0 here? How about this? The 0 polynomial. 0 is an element of W, since if we take 0, as a function, the 0 function, and let it act on 3, we get 0 again, right? And here, if you want me to put a tilde on this and say 0 tilde is equal to 0 times x squared plus 0 times x plus 0 or something like that. I don't know. I just don't do the tilde and I just write 0. And it's not usually confusing. It's probably more confusing since I wrote these tildes. Let me... 0's in there. All right? Oh, so therefore, W is not empty. So what's next? 3, we should consider what? F of x and g of x in W. And take a real number C. Right? what do we need to, we need to check that, how about f plus g? If we calculate f plus g of 3, so by the way, guys, what I'm really advocating here is that we look at polynomials as functions. It's just convenient. You'd be like, well, what else would you do? Fair enough. So f plus g of 3, how do we define that? Remember, it's, right, f of 3 plus g of 3, but we know by assumption, right, we're assuming that f and g are in W, so that means that f of 3 is 0, g of 3 is 0, right? So this is 0 plus 0, which is, by the way, 0. So that tells me, therefore, f of x plus g of x is in W. And what if we look at c times f of 3? What's that give us? Again, definition, pre-calculus stuff, college algebra, what do you want to call it? C times f of 3, right? But f of 3 is 0, c times 0, 0. So therefore, c times f of x is in W, right? So we have shown that W is closed under vector addition and scalar multiplication. It's a subset of the vector space of polynomials. It's non-empty. All of these things together give us, by the subspace test theorem, right? Hence, W is a subspace of R of x less than or equal to 2 by subspace test theorem, by subspace theorem. So, great. We do all of this, and yet we have no better sense of what W is. Am I right? So what are the elements of W? I mean, great, we've proved it's a subspace. We still don't really understand what it is, do we? Can you guys tell me how would we actually understand the structure of W more deeply? Not really linear algebra, you know, just basic pre-calculus stuff. What does it mean if we have a polynomial and we have this, right? What does that say about f of x? How about factor theorem, right? That says that that's equal to x minus 3, right, times g of x. But this is an element of, you know, it's a quadratic, right? So what's that say about the g of x? What's g of x have to look like then? When I multiply this thing out, it has to have the form, you know, a2x squared plus a1x plus a naught. That leaves, I mean, what's the degree of the other factor? The sum of the degree of x minus 3 and g has to be 2, right? I guess it could be less than 2, but at most 2. So that means that g of x has to have the form ax plus b, right? So in fact, we could write this, W is equal to x minus 3 times ax plus b, such that a and b are real numbers. Here I'm using polynomial theory, college algebra, if you will, factor theorem. And just common sense degree counting stuff, yeah? Yep.
How did you decide to multiply that x minus 3 on the top row?
Factor theorem. So if f of x is in W, then f of 3 is equal to 0. So this right here is vector theorem from college algebra. If we have f of c is equal to 0, that means that x minus c is a factor in the polynomial. Yeah. Yeah.
Number 2, proving that it's not, why did you choose 0?
Oh, it's just a choice. You could just as well have said, well, x minus 3 quantity squared, right, is equal to x squared minus 6x plus 9. That's an element of w, since 3 minus 3 squared is equal to 0, right? So therefore, x minus 3 squared is in w. 0 is just our typical, it's our go-to choice. It's just customary to look for 0, but you can look for other things. And again, like I said, the benefit of looking for 0 is if it's a non-example, game over. If you can't find a 0, you violated Axiom 3. So you've proved it's not a subspace. By the way, that's the other main point of knowing the definition is if you can show that any one of those axioms doesn't hold for your example, it's not a vector space. So that it's important to know all of them so you know all of the options for, denying something citizenship into the world of vector spaces. Yeah.
So can you just explain what it means to be a subspace again, just kind of in general?
Oh, yes, a subspace. So there's a universe. The universe is a given vector space. So vector space V over a field F. This is your universe, right? W is a subspace if it's something like inside here. If it's some subset of V, which itself is a vector space with respect to the addition and scalar multiplication of the universe in which it lives. So it's a smaller set of a vector space which still behaves like a vector space in the sense that you take the sum of things, it's again in there. Let me be more geometric for a second here. In R3, we have two kinds of, well, really, here's R3, a picture of R3, calculus 3 style, yeah, X, Y, Z. There are really kind of two interesting kinds of subspaces, right? The one kind of subspace, well, there's the boring one, which is just the origin by its lonesome, right? The other kind of subspaces you have are just lines through the origin. Something like W is the span of V not equal to 0. That lines through the origin are subspaces of R3. Right? 0 is the subspace of R3. All of R3 is a subspace of R3. But then there's one other interesting thing we've talked about some about also. There are things like, and now my picture gets too busy, but there's also planes. Something like this would be, for example, the solution set of x plus y plus z equals to 0. The solution set to that defines a vector space in R3 with normal 1, 1, 1. So for R3, if we think about the vector space R3, which is a good place to think about, there really are 4 kinds of subspaces. The 0 subspace, lines through the origin, planes through the origin, and the whole space, and that's it.
Sounds like we have a bell.
Sounds like somebody's like tuning a piano or something, yeah?
So what if it's the plane of the line is not through the origin?
Maybe that's like a code blue in some nursing lab or something. What is that?
What if the planar line is not through the origin?
If the planar line is not through the origin, then it doesn't contain 0. So with respect to the standard vector space structure, that wouldn't be a subspace. However, there is a non-standard addition of vectors we could give with which a plane not through the origin could be made into a subspace. But it wouldn't be a subspace of R3 with the standard vector space structure. That's a second order comment that I'm just making there. Okay, so look, you're like, well, this is kind of weird the way you did that. Is there some other way? Yes. You could just brute force attack it, right? You're looking for the set ax squared